Hello, my friend, and welcome. Tonight, we're exploring the science of light, the strange, beautiful thing that lets you see the universe at all. So get comfortable, relax, and let these quiet ideas carry you gently into sleep. Chapter 1. What light really is. The quiet mystery all around you. Light is so familiar that it can seem almost too ordinary to deserve wonder. It fills rooms, pours through windows, turns morning into day, and allows the entire visible world to appear before you with such ease that it rarely feels like a physical phenomenon at all. Most of the time, light does not announce itself as a scientific mystery. It just seems to be there, quietly making everything else possible. And yet, when physics began to ask what light actually is, the answer turned out to be far stranger and more beautiful than common sense would ever suggest. Light is not merely brightness. It is not just what comes from the sun or a lamp. In modern science, light is a form of electromagnetic radiation, part of a much broader family of phenomena that also includes radio waves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. What the human eye calls visible light is only a small slice of that greater spectrum. That simple fact already changes the way one can think about the world. The room around you is not only filled with the light you can see, it is also crossed by other forms of electromagnetic radiation that your eyes cannot detect. Signals for communication, heat radiated by warm objects, and high-energy radiation from violent cosmic events all belong to the same deeper category. Visible light is not separate from the rest of nature. It is one narrow band inside a larger, continuous spectrum. Human vision, remarkable as it is, does not reveal all light. It reveals only the small range of wavelengths to which our eyes evolved to respond. The universe itself is richer than sight alone. For a long time, people tried to understand light using the models most available to them. Some imagined it as a stream of tiny particles. Others thought of it as a wave spreading through space. Both ideas captured something important, yet neither was complete on its own. One of the great achievements of physics was discovering that light does not fit neatly into the categories that ordinary objects do. It is not like a pebble, and it is not like water in a pond, although each comparison can be useful for certain purposes. Light behaves in ways that reveal both wave-like and particle-like properties. This is not because science is confused, but because nature at a fundamental level does not always resemble the tidy divisions of everyday intuition. When scientists describe the wave-like nature of light, they mean that light has properties such as wavelength and frequency, and that it can interfere and diffract. Interference means that light can combine with itself in patterns of reinforcement and cancellation, much like overlapping ripples. Diffraction means that light can spread when it passes through narrow openings or around edges. These behaviors are not just abstract textbook details. They are direct clues that light is not simply a beam of little pellets flying through empty space. Wave behavior explains why light can form spectra, why it can bend in characteristic ways, and why many optical instruments work at all. It tells us that light has rhythm, structure, and pattern, and yet the particle side is equally real. In modern physics, the particle of light is called the photon. A photon is not a tiny glowing marble, but a quantum of electromagnetic energy. The idea emerged most powerfully when scientists studied situations in which light interacts with matter in discrete, indivisible amounts. One of the most famous examples is the photoelectric effect, in which light striking a material can eject electrons. What mattered in that effect was not simply how bright the light was, but the energy carried by individual quanta of light. This helps show that light must sometimes be treated as being delivered in specific packets, rather than as a smooth, continuous flow. That realization became one of the foundations of quantum physics. This does not mean that light is sometimes secretly a wave and sometimes secretly a particle in the ordinary sense. It means that light belongs to the quantum world, where the old categories inherited from daily life are no longer enough. In some experiments, the wave description is essential. In others, the photon description is unavoidable. Both are valid ways of describing the same underlying reality, depending on how light is being generated, measured, or made to interact with matter. This is one of the quiet lessons of modern physics. Nature is under no obligation to fit the first language humans invented to describe it. The universe can be understandable without being simple in the ways our intuition first expects. Another remarkable feature of light is that it travels at a special speed in vacuum, a speed so fundamental that it is built into modern physics itself. This is not merely the speed of something moving very fast. It is a central constant of nature, woven into the structure of electromagnetism and relativity. In vacuum, light travels at a fixed speed, and that fact reshaped the human understanding of space and time. It means that light is not just something we happen to see. It is also part of the deep architecture by which the universe is organized. Even when later chapters explore this idea more fully, it is worth noticing here how extraordinary it is that something so ordinary in daily life turns out to occupy such a central role in the laws of nature. The speed of light also helps explain why seeing is never exactly the same as instant knowing. Light takes time to travel. For objects around you on Earth, that delay is so tiny that it goes unnoticed, but on larger scales, it becomes profound. Sunlight takes time to reach Earth. Light from distant stars and galaxies has traveled across enormous stretches of space before entering a telescope or an eye. To see the universe is always, in some sense, to look into the past. Even the most immediate act of sight depends on something arriving. The visible world is not simply present, it is delivered. That makes light more than illumination. It is a messenger. If light is electromagnetic radiation, then what does that actually mean? At a classical level, it means that light can be described as linked oscillations in electric and magnetic fields propagating through space. That insight reached one of its most powerful forms in the work of James Clerk Maxwell, whose equations showed that electricity and magnetism are not separate phenomena, but deeply connected aspects of a single field. Those equations predicted waves moving through space at exactly the speed already known for light, revealing that light itself is electromagnetic. This was one of the great unifications in science. It took what had once seemed like separate topics and showed them to be expressions of the same underlying reality. Light was no longer just a thing seen by the eye. It became part of a universal physical framework. But even that classical triumph did not finish the story. Quantum theory later showed that light is quantized, that its energy comes in discrete units associated with photons, and that many of its interactions with matter can only be understood through this quantum description. This is one reason light has played such a special role in the development of science. Again and again, it has forced humans to rethink their deepest assumptions. It challenged old theories of vision. It helped unite electricity and magnetism. It helped launch quantum mechanics. It helped reveal relativity's strange consequences. Few subjects in physics have been as consistently transformative. To ask what light is has often meant asking what reality itself is like at its most basic level. There is also something elegant about the way light links the abstract and the intimate. At one extreme, it belongs to grand theories about fields, quanta, and cosmic structure. At the other, it is the reason leaves glow green, clouds burn orange at sunset, and distant stars become visible across the dark. The same phenomenon that can be described through advanced physical theory is also the phenomenon that makes the world visually tender. Science does not remove that tenderness. If anything, it deepens it. To know that color begins in wavelength, that vision begins in interaction, and that the warmth of a bright morning is part of the same electromagnetic story as the light of remote galaxies is not to diminish experience. It is to quietly enlarge it. Even the energy of light carries this double character of familiarity and strangeness. Different kinds of light correspond to photons carrying different amounts of energy. Higher frequency light carries more energy per photon than lower frequency light. That is why blue light and ultraviolet light differ from red light and infrared, not only in appearance or in visibility, but in the energy involved in their interactions with matter. This matters in everything from biology to astronomy to technology. It shapes how materials absorb light, how detectors are designed, and how living tissues respond to radiation. The visible colors that seem so soft and simple to human awareness are also part of a measurable physical scale rooted in frequency and energy. So what is light in the quietest and clearest sense? It is a form of electromagnetic radiation. It is the visible part of a larger spectrum. It behaves with both wave-like and particle-like features. It is carried in quanta called photons. It travels through vacuum at a fundamental speed. It brings information across space. It connects ordinary sight to the deepest theories of physics. And it reminds us that reality can be both intelligible and surprising at once. None of this makes light less gentle in daily life. The sunlight falling on a wall remains sunlight on a wall. A lamp in a quiet room remains a lamp in a quiet room. But behind that gentleness stands a phenomenon of astonishing depth. Perhaps that is one reason light has fascinated humanity for so long. It is everywhere, yet never fully exhausted by familiarity. The more carefully science studies it, the more it becomes a doorway into larger truths. It reveals that seeing is not passive, that emptiness is not truly empty of structure, and that the world around us is woven from patterns far more subtle than the eye alone can tell. Light does not merely brighten the universe for us. In a very real way, it teaches us how the universe is built. And for now, that is enough to rest with. The world does not need to become less mysterious for it to feel gentle. You can let the day grow quiet, knowing that even the softest glow around you is part of something vast, ordered, and deeply beautiful. Chapter 2. From Fire to Physics: How Humans Learn to Understand Light. Long before light became a subject of physics, it was already one of humanity's deepest companions. Fire made warmth possible after sunset, turned darkness into a visible world, and likely shaped some of the earliest feelings of safety, ritual, and shared attention. Sunlight marked the rhythm of waking and sleeping, guided travel, changed the appearance of seasons, and made the sky itself a source of wonder. At first, light was not something people explained in scientific terms. It was something they lived inside. The earliest human relationship to light was practical, emotional, and symbolic before it became analytical. Only much later did people begin asking a more difficult question, not merely how light helps us see, but what light actually is, how vision works, and whether brightness belongs to the eye, the object, or the space between them. In the ancient world, one of the greatest obstacles to understanding light was that human experience can easily make vision seem immediate and effortless. Because seeing feels natural, it is not obvious where the process begins. Some early Greek thinkers imagined that sight involved something reaching outward from the eye toward the world. Euclid's work on optics treated visual rays in a geometrical way and helped establish the mathematical study of vision and perspective, even though the underlying picture of how seeing happened was still incomplete. Ptolemy later carried optical study further and made careful investigations of visual perception and refraction. These efforts were important not because they solved the problem fully, but because they treated light and sight as subjects that could be analyzed, measured, and reasoned about. That was a major step. Human beings were beginning to move from myth and intuition toward disciplined inquiry. Yet the decisive change came much later, when scholars in the medieval Islamic world examined vision more critically. Ibn al-Haytham, known in the Latin tradition as Al-Hazan, played a central role in that transformation. In his book of Optics, he rejected the idea that vision occurs because the eyes send something outward. Instead, he argued that light reflected from objects enters the eye, and that seeing is therefore based on passive reception rather than active emission. This seems obvious now, but at the time it was a profound correction. It shifted the problem of vision away from speculation about the eye projecting rays and toward the physical behavior of light itself. Just as importantly, Ibn al-Haytham combined mathematical reasoning with close attention to experiment and observation. In the history of optics, this marks one of the clearest early examples of a more recognizably scientific method being applied to light. That change mattered for more than just the theory of sight. Once light was treated as something that travels from sources or reflects from objects into the eye, optics could develop as a science of paths, angles, media, and images. Mirrors, lenses, shadows, and refraction were no longer just visual curiosities. They became clues. The visible world itself became a laboratory. Over time, this encouraged more systematic thought about how light moves in straight lines, how it reflects from surfaces, and how it bends when it passes between different transparent materials. In other words, the study of light began to separate itself from the study of perception alone. Instead of asking only how humans see, scholars increasingly asked what light does before it ever reaches the eye. That shift was essential, because modern physics would eventually depend on precisely that distinction. By the early modern period, this growing tradition of optical investigation met a broader transformation in science. The natural world was being studied with increasing mathematical discipline, and light became one of the clearest testing grounds for the new method. Isaac Newton stands at the center of this stage. Through experiments with prisms, he showed that white light is not pure and simple in the way earlier thinkers often assumed. It can be separated into colors, and those colors are not created by the prism, but revealed by it. This was a turning point because it changed the status of color. Color was no longer just a subjective decoration added by perception. it became a property connected to light itself. Newton's optics also exemplified a style of research in which carefully arranged experiments could expose hidden regularities in nature. His work did not settle every question about light, but it made optics one of the most successful fields of experimental science. Newton also favored a corpuscular view, treating light as if it were composed of tiny particles. This idea had advantages. It matched the apparent straight-line travel of light and gave a seemingly natural account of reflection. For a time, Newton's authority helped this picture dominate much of European science. But scientific history is rarely a single straight victory. Even when a theory explains much, nature often leaves small difficulties behind. In the case of light, those difficulties slowly accumulated. Some optical phenomena were not easily captured by a simple particle picture. Meanwhile, another tradition, associated especially with Christian Huygens, suggested that light might instead be better described as a wave. In his treatise on light, Huygens developed a detailed wave theory and used it to derive the laws of reflection and refraction. The disagreement between Newton and Huygens was not just a quarrel between personalities. It was a sign that light was too subtle to surrender easily to one simple image. The wave view gained its strongest support in the work of Thomas Young. His interference studies showed that when light from a single source is split and then recombined, it can produce alternating bright and dark patterns. This behavior is naturally explained if light has wave-like properties, because waves can reinforce or cancel one another depending on how they line up. The significance of this was enormous. It meant that light could no longer be understood only through the visible path of a ray. It also had to be understood through relations of phase, overlap, and pattern. Young's work revived the wave theory and helped break the long dominance of the corpuscular model. Science was learning a humbling lesson. Even one of the most familiar features of daily life could behave in ways that defeated everyday intuition. As the 19th century continued, light became even more deeply woven into the fabric of physics. The question was no longer only whether light was made of particles or waves, but what kind of wave it might be. James Clerk Maxwell provided the next great synthesis. By developing a unified theory of electricity and magnetism, he showed that changing electric and magnetic fields could propagate through space as waves. The speed predicted by his theory matched the known speed of light, leading to the extraordinary realization that light itself is electromagnetic. This was one of the great unifications in science, a phenomenon once studied through vision, mirrors, and color was now recognized as part of a much broader field that also included electrical and magnetic behavior. Light was no longer just an optical subject. It had become a fundamental expression of the physical world. At that moment, one might have imagined the story was nearly complete. But the history of light has a way of unsettling every sense of completion. Classical wave theory explained a vast range of optical behavior with stunning success, yet new experiments at the beginning of the 20th century revealed cracks in the picture. One of the most important involved the photoelectric effect. Light falling on a metal could cause electrons to be emitted, but the result depended in a crucial way on frequency rather than brightness alone. Albert Einstein explained this by proposing that light could be treated as being delivered in discrete quanta of energy. For that work, especially for the discovery of the law of the photoelectric effect, he later received the Nobel Prize in Physics. The lesson was astonishing. The long argument between particle and wave had not ended with a simple winner. Instead, physics was being forced into a deeper and stranger understanding in which light could not be fully described by the ordinary categories inherited from common sense. So the history of light is not merely a history of one subject. It is almost a compressed history of science itself. It begins in immediate human experience, passes through philosophical speculation, grows through geometry and experiment, is refined by mathematical theory, and then opens into modern physics by repeatedly exposing the limits of earlier ideas. At each stage, people did not simply add more information. They changed the very questions they were asking. Early thinkers asked how sight works. Later investigators asked how light travels. Later still, physicists asked what kind of entity light is, how it relates to electricity and magnetism, and why it behaves differently at different scales of observation. The object of study remained the same, yet the intellectual world around it kept transforming. In that sense, the science of light is also the science of human self-correction. It shows how knowledge grows not by moving cleanly from ignorance to certainty, but by learning how to let inadequate pictures go. There is something quietly moving about that long journey. Human beings first sat beside fire without knowing what light was. They watched dawn return, saw reflections in water, noticed shadows, color, and stars, and for a very long time had only partial stories to tell about them. Yet across centuries, through many cultures, languages, and methods, those partial stories became more exact. Vision was separated from guesswork. Optics became measurable. Color became analyzable. Light became connected to electromagnetism, then to quantum theory, and with it to some of the deepest structures in science. What began as an everyday presence became one of the great teachers of physics. That may be one of the most remarkable things about human thought. The universe did not explain it to us all at once, but slowly, through patience, correction, and attention. And perhaps that is why the history of light feels larger than the history of a single discovery. It is a record of minds reaching outward through darkness, not perfectly, not quickly, but persistently. For all the distance between ancient firelight and modern physics, they belong to the same human effort to understand what surrounds us. When you think about that long arc, it becomes possible to feel both smaller and more connected at once. We live brief lives, yet we inherit questions that began long before us, and sometimes, for a moment, we get to see a little farther. Chapter 3. Light as a Wave. The Hidden Rhythm of the Electromagnetic World. When people first begin learning about light, it can seem natural to imagine it as a beam, almost like a stream of something moving from one place to another. That picture is useful in many everyday situations, especially when light appears to travel in straight lines and cast clean shadows. But the deeper study of optics revealed that light also behaves in a way that is far more rhythmic than that simple image suggests. In many important situations, light acts as a wave. This does not mean it is like water in every respect, or that it needs a material surface to ripple across. It means that light spreads through space with repeating structure, with patterns that can be described in terms of wavelength, frequency, phase, and amplitude. The wave picture became essential because it explains real behaviors that no purely simple ray picture can fully capture. A wave is in the most general sense, a traveling disturbance that carries energy and information. In the case of light, the classical description developed in electromagnetism shows that it consists of linked oscillations in electric and magnetic fields propagating through space. These oscillations do not sit still. They renew themselves continuously as the wave advances, carrying energy outward from a source. This is why the wave idea became so powerful. It allowed scientists to treat light not merely as brightness or illumination, but as a physical process with measurable structure. Once that happened, light could be compared across many different situations, from visible color to radio communication to the invisible radiation arriving from distant stars. Two of the most important wave properties are wavelength and frequency. Wavelength refers to the distance over which the repeating pattern of the wave completes one cycle. Frequency refers to how rapidly those cycles pass a given point. These properties are not decorative details. They are central to what kind of light one is dealing with. The electromagnetic spectrum is organized by differences in wavelength and frequency, and visible light occupies only a small portion of that larger range. The colors humans can see correspond to different wavelengths within the visible band, while infrared, ultraviolet, radio waves, X-rays, and gamma rays extend beyond it. The wave view therefore helps place visible light inside a much wider natural order. It reminds us that what human sight calls light is only one narrow window into a broader electromagnetic reality. One reason the wave description mattered so much historically is that waves can overlap. When they do, they obey the principle of superposition, meaning their effects combine. This leads to one of the most important phenomena in optics: interference. If two light waves meet in such a way that their peaks and troughs align favorably, the result is reinforcement, producing greater intensity. If they meet in opposition, they can reduce or cancel one another. This is not just a theoretical curiosity. It is direct evidence that light has wave-like character. The appearance of stable bright and dark interference patterns showed that light could not be understood only as isolated particles moving independently along straight tracks. Instead, light had to be recognized as something capable of building patterns through overlap and relation. The importance of interference goes beyond the famous laboratory demonstrations. It reveals something subtle about nature itself. Light is not only about where energy arrives, it is also about how different parts of a wave relate to one another in timing and structure. That is why phase matters. Two waves with the same wavelength and frequency can still produce different results depending on whether their cycles line up or are offset. This ability to produce reinforcement and cancellation is one of the deepest reasons wave language remains indispensable in optics. It captures a relational aspect of light that is invisible in ordinary experience, but decisive in precision science and technology. Spectroscopy, interferometry, and many optical instruments depend on exactly these wave-based effects. Closely related to interference is diffraction. Diffraction is the bending and spreading of waves when they encounter an obstacle or pass through an opening, especially when the size involved is comparable to the wavelength. In the case of light, diffraction shows that even when a beam seems sharp and straight, its behavior at edges and apertures is richer than simple geometry suggests. A narrow slit does not merely let light continue onward in a perfectly clean line. Instead, the wave spreads and forms patterns. This is one of the most elegant demonstrations that light cannot be reduced to straight rays alone. Diffraction places a limit on perfect focusing and perfect imaging, which is why it matters so much in telescopes, microscopes, cameras, and spectrometers. This also means that light as a wave sets physical limits on how precisely an optical system can resolve detail. In an idealized geometric picture, one might imagine a lens focusing light from a point source into a perfect point. In reality, diffraction prevents that exact perfection. The image formed has a finite spread because the wave nature of light cannot be ignored. This matters whenever scientists or engineers try to observe very small structures or distinguish objects that are very close together. The clarity of an image depends not only on the quality of the instrument, but on the fundamental wave behavior of light itself. So even in our best tools, nature quietly reminds us that visibility is shaped by physical law. Another crucial wave property of light is polarization. For many people, polarization seems like a technical extra, but it is actually a powerful clue about what sort of wave light is. Polarization describes the orientation of the electromagnetic field. Unlike sound in air, which is typically treated as a longitudinal pressure wave, light is a transverse electromagnetic wave, and that gives it polarization behavior. Polarized sunglasses provide a simple everyday example. They reduce glare by preferentially absorbing certain polarized components of reflected light. What appears in daily life as a comfort feature in eyewear is, in physical terms, direct evidence about the geometry of the wave itself. Polarization also plays a major role in imaging, materials analysis, astronomy, and the study of scattered light. The wave picture also helps explain why different kinds of electromagnetic radiation, though all part of the same spectrum, interact differently with matter. Because wavelength and frequency vary across the spectrum, different regions are suited to revealing different physical processes. Radio waves can travel long distances and are useful for communication. Infrared radiation is strongly associated with thermal emission from warm objects. Visible light is the narrow region to which human eyes respond. Ultraviolet radiation, X-rays, and gamma rays involve progressively higher frequencies and shorter wavelengths, making them useful in contexts ranging from imaging to the study of energetic cosmic events. The wave framework does not merely organize these forms of radiation into a chart. It reveals a unified family whose members differ through measurable patterns. This unification became one of the most beautiful results in physics when James Clerk Maxwell showed that electricity and magnetism are not separate domains, but aspects of a single electromagnetic field. In his theory, changing electric and magnetic fields sustain one another and travel through space as waves. The predicted propagation speed matched the known speed of light, leading to the realization that light itself is electromagnetic. That insight did more than explain an old mystery. It connected optics to a much broader structure in nature. Light was no longer just something involved in seeing. It became one expression of a universal field-based order that also includes radio waves and other forms of radiation beyond sight. The wave theory of light therefore did not stay confined to optics. It expanded into one of the central frameworks of physical science. Still, the wave description should not be confused with a claim that classical wave theory explains everything about light. Later developments in quantum physics showed that light also has properties that require the language of photons and quantized interactions. But that does not weaken the importance of the wave picture. It means only that light is more subtle than any single everyday analogy. For interference, diffraction, polarization, spectral structure, and the propagation of electromagnetic radiation across space, the wave description remains fundamental. It is one of the great achievements of science that light can be understood through multiple complementary frameworks, each revealing a different aspect of the same reality. In this chapter, the focus belongs to the wave side because without it, much of the hidden order of light would remain invisible to thought. There is also something quietly profound in the idea that light is rhythmic. The visible world often seems solid, stable, and immediate. Yet beneath that appearance lies oscillation, repetition, and propagation. What reaches the eye is not a static thing, but an arriving pattern. Color depends on wavelength. Clarity depends on diffraction limits. Reflection and glare can carry polarization. Spectra reveal themselves through interference and separation. The world we see is not simply sitting there waiting passively to be looked at. It is continuously being delivered through structured electromagnetic behavior. The wave picture helps make that delivery intelligible. It teaches that appearance is not superficial at all. It is the end result of deep physical regularities playing out across space. That is one reason the wave nature of light feels so elegant in the history of science. It took something once treated mostly as brightness and showed it to have measurable rhythm, hidden geometry, and lawful pattern. Through wave theory, light ceased to be only illumination and became a language of structure. It became possible to read matter, motion, temperature, and even the distant universe through the way electromagnetic waves behave. Human beings did not invent those rhythms. They discovered that the universe was already moving with them. Perhaps that is why the study of light so often feels larger than optics alone. It suggests that reality is not built merely from objects, but from relationships, patterns, and recurring forms that pass through the dark, whether we notice them or not. And there is a quiet comfort in that thought. Even when life feels scattered and unfinished, the world itself is full of lawful rhythms that continue without confusion. Light crosses space in ordered patterns, carrying structure through emptiness, and somehow those patterns become vision, knowledge, and meaning. We are small inside that immense procession, but we are not outside it. For a brief time, we are among the beings who can notice the waves passing through the universe and wonder what else they may be saying. Chapter 4. Light as a Particle, Photons and the Quantum Nature of Illumination. For a long time, the wave description of light seemed so successful that it was tempting to believe the story was complete. Interference, diffraction, polarization, and the broader electromagnetic spectrum all fit beautifully within the language of waves. Light appeared to be one of the great triumphs of classical physics, and yet, as often happens in science, the deepest problems did not arrive by destroying what had already been learned. They arrived by revealing that something important was still missing. In the case of light, that missing element emerged when physicists began studying how radiation is emitted, absorbed, and exchanged by matter on very small scales. The result was not a rejection of wave behavior, but the discovery that light also has a particle-like aspect that cannot be ignored. One of the most important clues came from the study of heated objects. Any object with a temperature above absolute zero emits electromagnetic radiation. A warm stove, a glowing metal filament, and the sun all radiate energy, but they do so in different ways depending on temperature. By the end of the 19th century, scientists had measured the distribution of this thermal radiation with great precision. Classical physics struggled to explain the full pattern. In particular, the old theory predicted too much energy at short wavelengths, leading to a contradiction with observation. Max Planck resolved this problem by making an extraordinary proposal. He suggested that the exchange of radiant energy between matter and radiation does not occur in an arbitrarily smooth and continuous way. Instead, it takes place in discrete amounts. This was the beginning of quantization, and although Planck himself did not immediately claim that light literally consisted of particles in the modern sense, his work opened the door to that possibility. The significance of Planck's idea is difficult to overstate. Classical physics had treated energy much like a continuously divisible substance. In that familiar picture, one could imagine energy flowing in any quantity, however small. Planck showed that at the microscopic level, nature does not always behave that way. Certain exchanges come in definite units. This was a radical shift because it suggested that smooth continuity, so natural in large-scale experience, might not hold at the foundations of physical interaction. Light was becoming one of the first places where the universe forced human thought beyond ordinary intuition. The next decisive step came from Albert Einstein. In his explanation of the photoelectric effect, he proposed that light itself can behave as if it is made of discrete packets of energy. This was more than a mathematical trick. It was a physical claim about the nature of radiation. The photoelectric effect occurs when light shines on a material, often a metal, and electrons are emitted. What made the phenomenon so important was that the outcome depended on the frequency of the light, not merely on its overall brightness. If the light's frequency was too low, increasing the intensity did not solve the problem. Electrons still would not be ejected. But if the frequency was high enough, electrons could be released, and increasing intensity then increased the number of emitted electrons rather than changing the basic threshold condition. Einstein explained this by treating light as consisting of quanta, later called photons, each carrying a definite amount of energy. A single electron could absorb the energy of a single photon. If that energy was sufficient, the electron could escape the material. If it was not sufficient, no amount of gentle accumulation from low-energy light would produce the same result. This was one of the great turning points in modern physics. The photoelectric effect showed that light could not be understood only as a continuously spread wave delivering energy evenly across space. In some interactions, light behaves as though it arrives in localized quanta. Einstein's explanation was so important that the Nobel Prize in Physics awarded to him recognized especially his discovery of the law of the photoelectric effect. That fact alone is a reminder that Einstein's scientific legacy extends far beyond relativity. In the history of light, his role was central in giving the particle picture a firm physical basis. The photon is the name given to this quantum of light. A photon is not a tiny hard speck in the ordinary mechanical sense, nor is it a miniature glowing bead traveling through darkness like dust in a beam. It is better understood as a quantum excitation of the electromagnetic field, carrying a definite amount of energy and momentum while having no rest mass. In modern physics, that language matters because it avoids misleading images from everyday life. The photon is real, but it is real in a quantum way. It belongs to the deep structure of field theory and quantum mechanics, where the categories inherited from common objects become only partially useful. Photons can be emitted, absorbed, counted, and detected individually. They carry energy in definite packets, and their interactions with atoms, electrons, and other systems reveal that discreteness very clearly. This particle-like description helps explain many physical processes. Atoms do not radiate arbitrary amounts of light whenever they please. Their electrons occupy quantized energy states, and transitions between those states involve the emission or absorption of photons with specific energies. That is why atomic spectra consist of distinct lines rather than continuous smears. The light emitted by atoms is structured because the allowed changes inside atoms are themselves structured. In this way, the particle nature of light is deeply tied to the quantized structure of matter. Radiation and atoms meet each other through exact exchanges. The universe at small scales is not vague in its bookkeeping. It is surprisingly precise. Another major confirmation of the photon concept came from the Compton effect. When high-energy light, such as X-rays, scatters from electrons, the scattered radiation emerges with a changed wavelength in a way that can be explained by treating the interaction as a collision involving a particle with momentum. Classical wave theory alone could not account for the observed shift in the same direct way. The Compton effect therefore provided powerful evidence that light quanta carry momentum as well as energy. This mattered because it showed that the particle description was not merely a convenient interpretation of one experiment. It had broader physical consequences. Light could push, transfer momentum, and behave in interactions as something more sharply individuated than a continuous wave spread. The idea that light carries momentum also helps explain radiation pressure. Even though photons have no rest mass, they can still transfer momentum when they are absorbed or reflected. This effect is usually very small in ordinary life, but it is measurable and real. It matters in sensitive experiments, in astrophysical environments, and even in proposed methods of spacecraft propulsion using light sails. The fact that illumination can exert pressure reveals something subtle and beautiful. Light does not merely reveal the world. It participates in it physically. It can move matter, however gently, and that makes the particle aspect of light more than an abstract theoretical refinement. Still, the arrival of the photon did not erase the wave nature of light. That is one of the reasons the quantum theory of light can feel so difficult at first. The wave picture remained indispensable for explaining interference, diffraction, and many propagation effects. The particle picture became indispensable for explaining emission, absorption, and certain interactions with matter. The universe did not choose one simple metaphor and reward human preference for clarity. Instead, it presented a phenomenon that requires complementary descriptions. In quantum mechanics, this is not treated as a flaw. It is part of the structure of the theory. Light is not sometimes really a wave and secretly actually a particle in the ordinary sense. Rather, the full quantum reality of light is richer than either classical image alone. Which aspect becomes most visible depends on how light is prepared, measured, and made to interact. This is why modern detectors can count photons one by one, while other instruments reveal interference patterns that are unmistakably wave-like. The result depends not on the universe contradicting itself, but on the fact that classical language reaches its limits in the quantum domain. Science did not fail when it discovered this. On the contrary, it became more honest. Instead of forcing reality into a single comfortable image, physics learned to describe nature in a way that preserved what experiments actually showed. That required a deeper humility. Light had once again taught human beings that the world is intelligible, but not necessarily in the first way the mind would prefer. There is another important sense in which photons changed science. Once light was understood in quantum terms, entirely new fields opened up. Quantum optics, laser physics, atomic spectroscopy, and later quantum information science all depend on the precise control and understanding of photons. Light became not only an object of explanation, but also a tool for probing the quantum structure of reality. The photon concept helped scientists understand why matter emits light in discrete ways, how detectors work, how atoms exchange energy, and how information can be carried with extraordinary precision. A great many modern technologies, from imaging systems to communication tools to experimental physics itself, rest on this quantum understanding. What makes the photon especially fascinating is that it brings together exactness and strangeness in equal measure. A photon has a definite energy. It can trigger a detector. It can be emitted in an atomic transition. It can transfer momentum. These are crisp physical facts. Yet, the deeper meaning of a photon cannot be captured by picturing a tiny bullet of light moving through empty space in the way a pebble moves through air. The particle language is necessary, but the old mechanical imagination is not enough. In the quantum world, something can be countable without being classically solid, localized in detection without behaving like an ordinary miniature object at all times. That is part of the intellectual beauty of modern physics. It teaches precision without promising simplicity. So the particle nature of light is not a denial of the wave chapter that came before it. It is the next layer of truth. If the wave description revealed the hidden rhythm of the electromagnetic world, the photon reveals the hidden discreteness of its exchanges. Light can spread like a wave through space, but it is absorbed and emitted in quanta. It can form interference patterns, yet arrive at a detector in individual events. It can illuminate a room softly and continuously to human experience, while, at a deeper level, being built from countless discrete acts of interaction. The smooth world of appearance and the granular world of quantum process are not enemies. They are two views of the same underlying reality, seen at different scales of thought. Perhaps that is why the photon carries such philosophical force. It reminds us that reality is not obligated to be shaped like our instincts. What seems continuous may be woven from indivisible exchanges. What seems simple may rest on structures so subtle that they reveal themselves only through patience, experiment, and revision. We live surrounded by light every day, and yet even that familiar presence turns out to be quantum at its core. There is something humbling in that. The ordinary world is never merely ordinary, and maybe that is part of the quiet comfort here as well. The universe does not become less beautiful when it grows stranger under close attention. It becomes deeper. The light that falls across a wall, a face, or an evening sky is not only brightness, but a procession of quanta crossing space with astonishing fidelity. We are brief observers inside that vast exchange, but for a little while we are able to notice that even illumination has a hidden inner life. Chapter 5: Color, Vision, and the Way Light Becomes Experience. color feels immediate. It seems to belong naturally to flowers, oceans, fruit, painted walls, evening clouds, and the shifting sky. In ordinary life, it is easy to speak as though color lives inside objects themselves, as though a leaf simply contains greenness in the same way it contains shape or weight. But the science of vision reveals something more subtle. Color is not a substance sitting on the surface of the world. It is an experience that arises when light of different wavelengths reaches the eye and is transformed by the nervous system into perception. In that sense, color is neither purely in the object nor purely in the mind. It emerges from an interaction between the physical structure of light, the reflective properties of matter, the biology of the eye, and the interpretive work of the brain. When light falls on an object, some wavelengths may be absorbed while others are reflected, transmitted, or scattered. The light that eventually enters the eye carries this altered pattern. A red apple does not create red light out of nothing. Under ordinary illumination, it reflects a range of longer visible wavelengths more strongly than many shorter ones, and that pattern becomes part of the information available to the visual system. The same object can look different under different lighting conditions because the incoming illumination has changed before reflection even begins. This is one of the first important lessons in color science. Color perception depends not only on the object, but also on the light source and the observer. The world is visible through relationships, not isolated properties. The physical journey of color begins when light enters the eye through the cornea and passes through the pupil and lens before reaching the retina at the back of the eye. The retina is not simply a passive screen. It is living neural tissue, part of the central nervous system, specialized to convert light into signals the brain can process. Within the retina are the photoreceptors, the cells that respond directly to light. Two broad classes are central here: rods and cones. Rods are highly sensitive and support vision in dim conditions, but they do not provide normal color vision. Cones are less sensitive in low light, but are essential for daylight vision, fine detail, and color discrimination. This means that the vivid world of daytime color is not merely a gift of incoming light. It depends on a specific biological system tuned to detect spectral differences in a particular way. Cones are especially important because human color vision depends on the fact that there are different classes of them, each with a different range of spectral sensitivity. These cone classes are often described as being most sensitive to short, medium, and long visible wavelengths. They are sometimes informally associated with blue, green, and red regions of the spectrum. Although that simplification can be slightly misleading because each cone type responds across a range, not to one perfectly isolated color. What matters is not that one cone sees one color and another cone sees a different one in complete isolation. What matters is the pattern of relative activity across these cone classes. The brain compares these responses, and from that comparison constructs the experience of hue. In other words, color is computed from differences in response, not read off directly from a single receptor. This idea lies at the heart of trichromatic theory, one of the foundational insights of color vision science. The theory explains how a wide range of perceived colors can arise from the combined activity of three cone classes. Different mixtures of cone stimulation can produce different color experiences, which is why devices such as screens can generate many apparent colors from combinations of a few primary light sources. Yet trichromatic theory is not the whole story. It explains an important early stage of color encoding in the retina, but later processing in the visual system organizes color information further through opponent mechanisms. The brain does not simply preserve raw cone signals. It transforms them into relational channels that support distinctions such as reddish versus greenish and bluish versus yellowish, as well as differences in brightness. This helps explain why some color pairings feel psychologically opposite and why certain combinations are not experienced in ordinary vision as single, stable colors. So even at the level of basic physiology, color is already more than wavelength. Wavelength matters, but perception is not a simple one-to-one translation from physical signal to conscious experience. The visual system processes contrasts, adjusts to lighting conditions, and compares signals across space and time. This is one reason color constancy is possible. A white sheet of paper can look roughly white in sunlight, shade, or indoor illumination, even though the actual wavelengths entering the eye from the paper may differ substantially across those situations. The brain uses context to stabilize appearance. Without that stabilizing ability, the visible world would change in a much more chaotic way whenever illumination shifted. Color perception therefore reflects both the physics of light and the active interpretive power of the nervous system. We do not merely receive color, we achieve it through neural processing. Rods introduce another layer of complexity. In low light, when cone activity becomes weak, rod vision dominates. Under those conditions, human color perception fades dramatically, and the world becomes closer to grayscale. This is why a richly colored landscape at dusk can slowly lose its vividness as darkness deepens. The eye has not become empty of information, but its most color-sensitive system is no longer operating in the same way. Rods are superb for sensitivity, but poor at delivering ordinary color experience. This shift reminds us that color is not an absolute feature of the external world waiting unchanged for discovery. It is conditional, dependent on illumination level, retinal physiology, and the state of adaptation of the observer. A scene may contain all the same objects at noon and at night, yet it becomes a different perceptual world because the biology of seeing has changed. The retina itself also does more than detect light. Signals from photoreceptors are processed through intermediate retinal circuits before reaching ganglion cells, whose axons form the optic nerve. By the time visual information leaves the eye, it has already been shaped by comparison, contrast enhancement, and channel separation. From there, signals pass through major relay structures and continue to the visual cortex, where further processing supports perception of form, motion, depth, and color. This means that color is not located at one single point in the system. It is built through stages. Light becomes photochemical change, then neural signaling, then structured visual representation, and finally conscious experience. The path from wavelength to perception is therefore not short or simple. It is a layered transformation carried out by living tissue. This helps explain why color vision can vary from person to person. Differences in cone pigments, retinal function, or downstream neural processing can alter how colors are discriminated. Color vision deficiency, often called color blindness in everyday language, commonly arises when one class of cone photopigment is absent or altered. In such cases, Some distinctions that are easy for many observers become difficult or unavailable. This does not mean the person sees nothing, but rather that the space of distinguishable color relationships is changed. The existence of these variations is scientifically important because it reveals how contingent ordinary color experience really is. What feels natural and obvious to one visual system is not necessarily universal. Human color perception is powerful, but it is also a biological specialization, not a perfect window onto all possible ways of seeing. There is also a philosophical quietness in the fact that color depends on both world and observer. On the one hand, it would be wrong to say color is merely invented, because it is constrained by measurable properties of light and matter. On the other hand, it would also be wrong to say color exists exactly as experienced independently of the visual system, because perception depends on cone sensitivities, neural comparisons, and contextual interpretation. Color belongs to an in-between realm. It is a lawful construction arising from contact between organism and environment. Science does not make color less beautiful by revealing this. It shows why beauty is even possible. The red of a sunset and the green of a leaf are not illusions in the trivial sense. They are real experiences built from physical regularities meeting biological structure. This is one reason color science feels so intimate. The previous chapters showed light as a physical phenomenon with wave-like structure and quantum behavior. Here, that same light enters a body and becomes appearance. It becomes the blue of distant hills, the warmth of amber light in a room, the pale silver of morning, the darkness of shadow deepened by contrast. The transition from radiation to experience is one of the most extraordinary transformations in nature. It happens so constantly that it is easy to forget how remarkable it is. Every moment of sight is a collaboration between the external world and the nervous system's power to interpret patterned light. We do not only live in a universe filled with radiation, we live in one that, through eyes and brains, can become luminous to itself. Perhaps that is why color can feel emotionally deeper than measurement alone. Science can describe wavelengths, photoreceptors, perhaps opponent processing, and visual pathways with extraordinary precision, and all of that matters. But those facts also point toward something quietly profound. The universe does not arrive to us raw. It arrives translated into experience by fragile living systems. Color is not just a property and not just a feeling. It is a meeting, and maybe there is comfort in that. The world you see each day is not separate from you, but formed in relation with you. For a brief time, matter shaped by evolution receives light from the wider universe and turns it into color, memory, and meaning. That is a small miracle of consciousness, gentle enough to happen every morning without asking for attention. Chapter 6. Reflection, Refraction, and Transparency. Why the world looks the way it does. The visible world does not appear to us simply because light exists. It appears because light meets matter in different ways, and those encounters shape what eventually reaches the eye. A mirror returns an image. A window allows a scene beyond it to remain visible. Water bends the appearance of a submerged object. Clouds glow softly instead of acting like polished metal, and a sheet of frosted glass lets brightness through while hiding detail. These differences arise from a small set of physical processes that govern how light behaves at boundaries and inside materials. Among the most important are reflection, refraction, absorption, scattering, and transmission. Together, they explain a great deal about why surfaces look shiny or dull, why lenses can focus, why some materials are transparent, and why others block sight completely. Reflection is one of the most familiar of these processes. When light encounters a surface, part of it may remain in the original medium and change direction. On a very smooth surface, this produces regular reflection, the kind associated with mirrors. In that case, light preserves enough directional order that an image can form. This is why a polished mirror can return a face, a room, or the sky with such precision. But most ordinary surfaces are not smooth at the microscopic level. Paper, stone, cloth, painted walls, and skin all have tiny irregularities. When light reflects from these uneven structures, it is sent outward in many directions, producing diffuse reflection rather than a clean image. That is why you can see a wall from many viewing angles without the wall behaving like a mirror. The surface still reflects light, but it scrambles the directional structure that would be needed for a sharp reflection. This difference between regular and diffuse reflection is part of what makes the world readable to vision. If every surface reflected light like a mirror, ordinary sight would be much more confusing. Shapes, textures, and positions would constantly be obscured by strong image-like reflections of other things. If nothing reflected light at all, most objects would remain dark to us unless they emitted light themselves. Instead, the world occupies a rich middle ground. Many materials reflect enough light to be seen clearly, but in a scattered and softened way that reveals form without turning every surface into a specular image. Much of visual life depends on this balance. The appearance of wood, leaves, paper, cloth, stone, and skin is deeply shaped by the fact that they reflect broadly rather than perfectly. Refraction explains another large part of visual experience. When light passes from one medium into another, such as from air into water or from air into glass, its speed changes and its direction usually changes with it. That bending is refraction. It is why a straw in a glass of water can look displaced, why lenses can bring light to a focus, and why the apparent position of an object can differ from its true geometric location when viewed through a transparent substance. Refraction is not a rare optical trick. It is one of the most common ways the world shapes light before it reaches us. The eye itself depends on refraction. The cornea provides most of the eye's refractive power, and the lens further adjusts focus so that an image can form on the retina. Clear vision is therefore not simply a matter of having sensitive photoreceptors. It requires the incoming light to be bent into the right paths before detection begins. Lenses make the role of refraction especially clear. A curved, transparent material can redirect incoming light rays so that they converge or diverge in controlled ways. This is the basis of eyeglasses, cameras, microscopes, telescopes, and the lens inside the eye itself. Refraction is therefore one of the main reasons the universe becomes available to careful observation. Without it, there would be no ordinary focusing, no optical correction for vision, and no great extension of sight through instruments. A telescope depends on the controlled steering of light. So does a microscope. Even a simple droplet of water can behave like a tiny lens. The same physical law that makes a fish look shifted beneath the surface also helps reveal bacteria, distant galaxies, and the printed text on a page. Transparency seems simple at first, but scientifically it is subtle. A transparent material is one that allows light to pass through with relatively little absorption and relatively little scattering, at least for the wavelengths under discussion. That last condition matters because a material can be transparent in one region of the electromagnetic spectrum and not in another. The atmosphere, for example, is transparent enough to visible light that the ground is illuminated by the sun, yet it does not transmit all wavelengths equally. Some wavelengths are strongly absorbed by components such as water vapor and other atmospheric constituents. This reminds us that transparency is not a permanent label attached to an object in every context. It is a wavelength-dependent property arising from how light interacts with the internal structure of matter. Glass is a familiar example because it is transparent to visible light while still influencing that light through refraction and partial reflection. A clean pane of glass may seem almost invisible when looked through directly, yet it can also show a faint reflected image depending on angle and lighting. This is a reminder that transmission, reflection, and absorption are not mutually exclusive categories in practice. A single material can do more than one thing at once. Some of the light passes through, some reflects, and some may be absorbed. That is why windows can both reveal a landscape and show a dim overlay of the room behind you. It is also why optical engineering often focuses on controlling surfaces carefully, for example by using coatings that reduce unwanted reflection and improve transmission. The visible world is full of such compromises. Opacity, by contrast, occurs when light is either absorbed strongly, scattered strongly, or both, so that clear transmission does not occur. A block of wood does not let you see through it because visible light does not move through its internal structure in an orderly enough way to preserve an image. The light is absorbed, reflected, and scattered in ways that prevent transparent passage. Frosted glass sits in an interesting intermediate region. It transmits light, but the transmission is so heavily scattered that detailed images disappear. Brightness comes through, but directional information is lost. This distinction is important because seeing through something does not depend only on whether light gets through at all. It depends on whether the spatial order of that light survives the journey. Transparency is therefore not merely about passage. It is about preserved structure. Scattering is especially important in the appearance of the natural world. It helps explain why clouds often look white, why haze softens distant landscapes, and why some materials look translucent rather than transparent. When light encounters particles, droplets, or structural irregularities, it can be redirected in many directions. If that redirection is strong enough, images blur or vanish. A cloud does not behave like a clear window because the countless water droplets inside it scatter light extensively. Low, thick clouds therefore reflect much of the incoming solar radiation, while thin, high clouds transmit more light and interact differently with the radiation balance of the atmosphere. The visual softness of clouds is not merely aesthetic. It is a consequence of large-scale scattering. The atmosphere itself also shapes what we see through scattering and transmission, which is one reason different wavelengths can reveal different aspects of Earth and space. Reflection and refraction also combine in some of the most beautiful familiar phenomena. Rainbows arise through refraction, internal reflection, and dispersion inside water droplets. The apparent shimmer of a pond, the brilliance of cut glass, the sparkle of ice, and the changing brightness of polished metal all depend on how surfaces and materials guide light differently. Even the distinction between glossy and matte paint is largely a story about reflection and surface microstructure. The visible world looks varied, not because light changes its fundamental nature from place to place, but because materials meet that light with different internal organization and surface geometry. Matter edits illumination. The eye receives the edited result. That is much of what vision consists of. There is also a deeper point here about appearance itself. Objects do not simply present their essence directly to sight. What we see is mediated by lawful interactions between light and material structure. A polished mirror reveals one kind of order, a leaf another, a pane of glass another, and a cloud yet another. The world becomes visible through transformation. Light is reflected, bent, delayed, scattered, transmitted, and partially lost. The visible scene is the end result of these negotiations. That does not make vision less real. It makes it more physically grounded. Appearance is not a superficial layer floating above reality. It is reality meeting light under definite laws. This chapter also completes an important arc from the previous ones, without repeating them too heavily. Earlier, light was treated as a physical phenomenon with wave behavior, quantum discreteness, and the capacity to become color through the nervous system. Here the focus is different. The question is not mainly what light is in itself or how the eye encodes it once it arrives, but what happens in between. Reflection, refraction, transparency, scattering, and absorption are the middle processes that shape visibility before sight becomes perception. They explain why the world has texture instead of perfect shine, why lenses can focus, why windows can both reveal and reflect, and why seeing through a material depends on preserved directional order as much as on simple passage. Perhaps that is one of the quietest truths in optics. The world looks the way it does not because sight passively receives reality, but because light and matter are always in conversation. Every surface answers illumination differently. Every material edits the path of what enters it. And from those countless interactions, the visible world is continuously assembled around us. There is something gently existential in that. What we call appearance is not false, but relational. The universe becomes visible through encounters, through boundaries, through changes of path. And perhaps human life is not so different. We too are shaped by what passes through us, what reflects from us, and what we allow to travel onward with its form still intact. Chapter 7. The Speed of Light, the Universe's Great Limit. The speed of light is often introduced as if it were simply the fastest speed in nature, a remarkable number attached to an already remarkable phenomenon. That is true, but it is not deep enough. In modern physics, the speed of light in vacuum is not important merely because light happens to move that fast. It is important because this speed is woven into the structure of space, time, causality, and measurement itself. In the International System of Units, the meter is defined through the exact value of the speed of light in vacuum, which reflects how fundamental this constant has become in physics. For much of human history, light seemed instantaneous. In everyday life, it certainly feels that way. A lamp is switched on, and the room appears bright at once. The sun rises, and the landscape is illuminated without any noticeable delay. Since the travel time of light across ordinary earthly distances is so small, early observers had little reason to suspect that light took time to move at all. But nature often hides its deepest truths behind the limits of ordinary perception. Once astronomy became precise enough, Scientists began to realize that light does not arrive infinitely fast. It travels very quickly, but it still travels, and that means it needs time. That discovery changed far more than optics. If light takes time to move, then seeing distant things means seeing them as they were when the light began its journey, not as they are now in any immediate sense. In astronomy, this becomes profound. Light from the sun takes time to reach Earth. Light from distant stars takes much longer. Light from remote galaxies can travel for immense spans of time before arriving at a telescope. This is why astronomy is inseparable from history. To observe the universe is to receive delayed messages. NASA's astronomy explainers emphasize exactly this point. Because light has a finite speed, looking farther into space means looking farther back in time. Before relativity, one might have imagined that the speed of light was simply a very high speed that could be added to or subtracted from other motions in the usual way. If a source moved toward you, perhaps the light would be expected to arrive faster. If it moved away, perhaps slower. But one of the central discoveries behind special relativity is that the speed of light in vacuum has the same value for all inertial observers, regardless of the motion of the source or the observer. Einstein Online, a scientifically curated educational resource from the Max Planck Institute for Gravitational Physics, states this plainly. In special relativity, the value of the speed of light is independent of the motion of light source or observer. That principle is not a minor correction to older mechanics. It is the beginning of a new framework for reality. Once that constancy is accepted, familiar ideas about time and space can no longer remain untouched. In classical thinking, time flows the same way for everyone, everywhere, and distances are assumed to be fixed independently of the observer's motion. But if light speed is constant for all inertial observers, then measurements of time and length must adjust instead. This is where special relativity begins to reshape intuition. Moving clocks run differently from stationary ones, and distances along the direction of motion are not the same for all observers. These effects are not philosophical decorations added to physics. They are required if the speed of light is to remain invariant. Einstein Online explains this through thought experiments, such as the light clock, where the constancy of light speed leads directly to time dilation. So the speed of light is not just a property of a traveling beam. It functions as a conversion factor built into spacetime itself. It links temporal intervals and spatial intervals in the relativistic description of the world. That is why it appears so centrally in modern theoretical physics, and why it became suitable for defining the meter in the SI system. This is an extraordinary status for a quantity once thought of merely as a feature of illumination. The speed of light became one of the constants through which modern physics describes what can happen, how influences propagate, and how measurements made by different observers fit together consistently. Another way to understand its importance is through causality. If there is a maximum speed at which signals or interactions can travel through vacuum, then this speed limits how quickly one event can influence another. Light is not the only thing bound by that limit. In relativity, no usable signal or causal influence can outrun it through vacuum. This means the speed of light sets the pace at which the universe can communicate with itself. There is no immediate universal now connecting distant locations in the old intuitive sense. Instead, there are limits on simultaneity, on influence, and on what can be known directly across great distances. The universe is connected, but not instantaneously. Its order unfolds through finite propagation. This finite limit also explains why the concept of a light year is so useful. A light year is not a unit of time, but a unit of distance. The distance light travels in 1 year. NASA's explanations of cosmic distance use this idea because it naturally captures the scale of interstellar and intergalactic space. When the distances become enormous, ordinary everyday units become cumbersome, but light travel distance remains meaningful because it links space to the time required for information to cross it. In effect, the vastness of the cosmos is often measured by how long reality takes to arrive. There is also a quiet conceptual elegance in the fact that light's speed seems so enormous on human scales, and yet still so limiting on cosmic ones. Across a room, light feels instantaneous. Across the solar system, its travel time becomes noticeable. Across the galaxy, it becomes vast. Across the observable universe, it becomes one of the main reasons astronomy is a study of the deep past. The same finite speed that looks almost infinite in daily life becomes a reminder of separation when distances grow large enough. It is one of the most striking cases in science where a single fact changes character entirely depending on scale. Special relativity alone already makes the speed of light fundamental, but the story becomes even richer when gravity enters. Einstein's later work on general relativity did not abolish the importance of light speed. Instead, it placed that importance inside curved space-time. Einstein Online notes that special relativity provides a new framework when gravity is excluded, and that Einstein later unified gravity with relativistic ideas of space and time. In general relativity, light still plays a central role in defining how causal structure works locally, even though gravity can curve the paths that light follows. Light does not cease to be fundamental when space-time becomes dynamic. If anything, its importance becomes even more geometric. It is also worth noticing that the speed of light is specifically the speed of light in vacuum. In materials such as glass or water, light travels more slowly because of the way electromagnetic waves interact with the medium. This distinction matters. The fundamental constant of relativity concerns vacuum, not the reduced speeds found in matter. Everyday optical effects, such as refraction, depend on that difference, but the deeper relativistic role belongs to the invariant vacuum speed. That is the value fixed exactly in the SI system and used throughout fundamental physics. All of this helps explain why physicists do not speak of the speed of light merely with admiration, as if it were just impressively large. They speak of it with structural seriousness. It is part of the grammar of nature. It determines how electromagnetic radiation propagates in vacuum, how space-time intervals are related, how observers in motion compare measurements, how causal order is constrained, and how astronomy becomes a study of the past. The speed of light is therefore not one fact among many. It is one of the great organizing principles in modern science. This chapter also sits differently from the earlier ones. Before this point, light was explored as wave, as quantum, as color, and as the partner of matter in reflection and refraction. Here, the focus is not mainly on what light looks like, how it interacts with surfaces, or how the eye turns it into experience. The focus is on limit. The speed of light marks a boundary written into nature itself, a boundary that organizes what can be measured, what can be connected, and what can ever arrive in time. That is why this chapter belongs at the center of the larger story. The science of light eventually becomes the science of the universe's timing. Perhaps that is one of the strangest and most beautiful consequences of this idea. Reality is not delivered to every place all at once. Even the universe must wait for its own messages to travel. The stars do not appear to us in immediate presence, but through patient delay, and what we call seeing is often the reception of something already gone. There is something quietly existential in that. We live inside a cosmos where distance and time are never fully separate, and where even light so fast on human scales cannot erase the deep spaciousness between things. And maybe that is also part of the comfort. The universe is not chaotic in its distances. It is ordered by limits, by lawful delays, by a speed that gives structure to vastness. We are small within that immense arrangement, but for a brief while we can understand that the night sky is not only beautiful, it is a conversation arriving slowly, exactly as fast as the universe allows. Chapter 8. Light and Relativity. How Motion and Gravity Change Illumination. In everyday life, light often seems stable. A lamp shines, a star glows, a beam crosses a room, and it is easy to imagine that the light itself simply carries on unchanged until it reaches an eye or an instrument. But relativity teaches something more subtle. Light is not only governed by its own properties. Its observed color, frequency, direction, and path can all depend on motion, gravity, and the geometry of space-time. This does not mean that light becomes unreliable. It means that illumination is shaped by the structure of the universe through which it travels. Once motion and gravity are taken seriously, light stops being merely what reveals reality and becomes one of the clearest ways reality reveals its deeper laws. One of the simplest relativistic changes to light is the Doppler effect. In general terms, the Doppler effect describes how the observed frequency of a wave depends on the relative motion of source and observer. In the case of light, this means that motion can shift the observed wavelength and therefore the observed color or spectral position of radiation. If source and observer move toward one another, the light is shifted toward shorter wavelengths and higher frequencies, which is called a blue shift. If they move apart, the light is shifted toward longer wavelengths and lower frequencies, which is called a red shift. This idea matters enormously in astronomy, where much of what is known about motion in the universe comes from analyzing how spectral lines are shifted from their expected positions. What makes the relativistic Doppler effect especially important is that it is not merely a copy of the everyday sound version. Sound depends on a medium such as air, and its Doppler behavior is described in relation to that medium. Light in vacuum is different. Its speed remains the same for inertial observers, so changes in observed frequency do not arise because the light is somehow moving faster or slower through empty space in the ordinary sense. Instead, the shift is tied to the geometry of space-time and the relative motion of observer and source within that structure. Einstein Online emphasizes that for light, the Doppler effect is one of the important consequences of relativistic physics, not just a familiar wave trick extended into a new setting. This is why redshift and blueshift are not just descriptive words in astronomy. They are direct signs that motion and space-time geometry are changing how radiation is received. There is another effect related to motion that is less widely known, but deeply important: aberration. Aberration means that the apparent direction from which light arrives can change depending on the observer's motion. In other words, Motion through space changes not only how frequent a light wave appears, but also where it seems to be coming from. This matters whenever light is being observed from moving platforms, including Earth as it travels through space. The visible sky is therefore not an absolutely fixed dome independent of motion. Its apparent geometry is subtly shaped by the state of movement of the observer. Even direction, which seems so straightforward in ordinary vision, becomes relational when relativity enters the picture. The universe is not simply seen from nowhere. It is always seen from somewhere, and that somewhere may be moving. Motion also affects intensity in certain relativistic contexts. When a source moves at very high speed relative to an observer, the emitted light can appear concentrated more strongly in the direction of motion. This is sometimes called relativistic beaming. It is especially important in astrophysics, where jets from energetic objects can look much brighter if they are directed partly toward us. This does not mean the source has become intrinsically more luminous in all directions. It means that motion changes how the radiation is distributed and received. Relativity therefore reaches beyond timing and measurement into appearance itself. It can make the same source seem different depending on how it moves through space-time relative to the observer. Gravity changes light in equally profound ways. In Newtonian intuition, gravity acts on masses, and light, having no rest mass, might seem exempt. General relativity changed that picture completely. In Einstein's theory, gravity is not primarily a pulling force acting in space. It is the curvature of space-time itself. Light follows the straightest possible paths in that curved geometry, which means its path can be bent by massive bodies. Einstein Online describes this as one of the basic predictions of general relativity. Light passing a massive body is slightly deflected. This is the foundation of gravitational lensing, one of the most powerful observational tools in modern astronomy. Gravitational lensing occurs when the gravity of a foreground mass, such as a galaxy or galaxy cluster, bends and distorts the light from a more distant background object. NASA explains that this bending can magnify, distort, and sometimes multiply the appearance of the background source. In some cases, it creates elongated arcs. In special alignments, it can produce rings or multiple images of the same object. This is not an illusion in the casual sense. It is a real consequence of curved space-time redirecting light along different paths. Gravitational lenses are valuable because they allow astronomers to study otherwise faint or distant objects and to map matter, including dark matter, through its gravitational influence on light. Here, relativity does not merely correct a detail of appearance. It becomes a method of seeing the invisible through the way light is bent. The deflection of light by gravity was one of the classic early tests of general relativity. Einstein Online notes that the famous eclipse observations in the early 20th century provided an early experimental check of the theory by comparing the apparent positions of stars near the sun with their positions when the sun was elsewhere in the sky. The observed shift agreed far better with Einstein's prediction than with the simpler Newtonian expectation. More modern techniques, including radio astronomy and high-precision space observations, have tested the effect far more accurately. What matters here is not just the historical milestone, but the conceptual shift. Gravity changes illumination by changing the geometry through which light travels. A beam of starlight does not move through a rigid and indifferent arena. It moves through a space-time that can itself be curved. Gravity also changes the frequency of light. This is called gravitational redshift. When light climbs out of a gravitational well, it is shifted toward longer wavelengths and lower frequencies. Einstein Online and ESA both describe this as a fundamental prediction of relativity. The key idea is that gravity affects time itself. Clocks deeper in a gravitational field run differently from clocks higher up, and since light is associated with frequency, the change in the rate of time is reflected in the observed radiation as well. Light escaping strong gravity is therefore received as redshifted. Conversely, light falling into a deeper gravitational region can be blue-shifted. This means gravity does not merely bend light's path. It also changes the measured rhythm of the light itself. This effect is not only theoretical. ESA notes that gravitational redshift was confirmed experimentally in precision measurements, and astronomical observations continue to test it in stronger gravitational settings. The result is conceptually beautiful because it ties together light, time, and gravity in one phenomenon. A change in gravitational environment becomes visible as a change in the received frequency of radiation. What an observer sees is therefore linked to how time flows where the light was emitted and how it traveled afterward. Illumination becomes a record of gravitational circumstance. Cosmological redshift adds another layer. NASA explains that as light travels across the expanding universe, its wavelength is stretched. This is different from the simpler local Doppler picture of a source moving through otherwise static space. In cosmological redshift, the expansion of the universe itself is central to the effect. Light arriving from distant galaxies can therefore be shifted toward the red, not only because of local relative motion, but because space-time expanded while the light was en route. This is one of the reasons the spectra of distant galaxies are so important in cosmology. Their shifted lines reveal not only the behavior of the sources, but the large-scale history of the universe through which the light has traveled. Taken together, these effects show that light in relativity is never merely a passive courier. Motion changes its observed frequency and apparent direction. Gravity bends its path and alters its frequency. Cosmic expansion stretches it across vast journeys. The same beam of radiation can therefore tell a story about velocity, gravitational environment, and the evolving structure of the universe all at once. That is what makes light such a powerful probe of reality. It does not only show us things, it carries within itself traces of the conditions under which it was emitted, the geometry through which it traveled, and the state of motion between source and observer. This chapter is also different in emphasis from the one before it. The earlier discussion of light's speed established a universal limit and showed why that speed is built into causality and space-time. Here the focus is not the constancy of that speed by itself, but what follows from relativity once that constancy is taken seriously. Light can be redshifted, blue-shifted, redirected, magnified, delayed, and distorted, not because it has ceased to obey law, but because it obeys deeper law than ordinary intuition first suggests. Relativity does not make illumination unstable. It makes it more informative. The universe writes its motion and its gravity directly into the light that reaches us. Perhaps that is one of the most beautiful consequences of relativistic light. We do not observe a fixed world from outside it. We receive signals that have been shaped by movement, curved by gravity, and stretched by cosmic history. Every distant glow arrives already carrying the story of space-time. Even a beam of light is not untouched by the structure of the universe. It is, in a quiet sense, a record of relation. And maybe that is part of the reflection this invites. What reaches us is never only what left the source, it is also what happened along the way. In that sense, the cosmos is not made of isolated things, but of journeys, distortions, and connections across depth. For a brief time, we are creatures who can read those altered beams and understand that the universe reveals itself not in spite of its vastness, but through it. Chapter 9. Light as a Tool: How Humans Use It to See the Invisible. Light does far more than illuminate what is already obvious. One of the greatest achievements of science was learning to use light not only as something to observe, but as an instrument of discovery. Once human beings understood that light could be controlled, focused, separated, guided, measured, and interpreted, it became one of the most powerful tools ever developed for investigating reality. With light, people learn to look deeper into the sky, farther into the past, and further into the hidden structure of matter and life. In that sense, light is not only what makes the world visible, it is one of the main reasons so much of the invisible world became knowable at all. One of the earliest and most transformative uses of light as a scientific tool was the telescope. A telescope does not create distant objects or bring them physically closer. What it does is collect more light than the human eye can gather on its own and direct that light into a form that can be examined more clearly. This simple idea changed human thought permanently. Once telescopes improved, the heavens stopped being a smooth decorative backdrop and became a domain of structure, motion, and history. Moons around other planets, the detailed surfaces of worlds in the solar system, distant nebulae, and eventually galaxies beyond the Milky Way, all entered human knowledge because light from those objects could be gathered and focused more effectively than the naked eye allowed. Modern astronomy goes much further than visible starlight. Telescopes can be engineered to detect forms of electromagnetic radiation outside the narrow range human eyes can see. Infrared astronomy is one of the clearest examples. NASA explains that infrared light allows astronomers to look through dust and to study otherwise hidden regions, such as star-forming clouds. It also helps reveal very distant objects whose light has been stretched into longer wavelengths during its long journey across the expanding universe. In this way, light becomes more than sight. By choosing different wavelengths, astronomers can make different aspects of the cosmos available. A dusty region opaque in visible light may open in infrared. A hot, energetic environment may stand out in other parts of the spectrum. The universe does not appear the same in every wavelength, and scientific observation takes advantage of that fact. At the opposite scale, microscopes turned light into a way of seeing the very small. The microscope made it possible to study cells, microorganisms, tissues, and fine structures that lie far below unaided vision. But microscopy is not just about magnifying. Magnification alone is not enough if detail remains blurred. What matters is resolution, the ability to distinguish nearby structures as separate. Authoritative microscopy references from the National Institutes of Health explain that in light microscopy, resolution depends strongly on wavelength and on how effectively the optical system gathers light. This means the very wave behavior of light sets the limits of what can be resolved. Even so, the light microscope became an indispensable biological tool because it transformed living tissues, cells, and microscopic organisms from hidden realities into observable ones. This is a profound shift in what it means to know something. Before optical microscopy, much of life's fine structure was simply inaccessible. Cells, organelles, microbial communities, and tissue organization were not absent from reality, but absent from ordinary human awareness. Light changed that. By using lenses, contrast methods, and controlled illumination, humans learned to make the small world yield information. Even when later tools such as electron microscopy reached beyond the limits of visible light, the conceptual revolution had already happened. Light had shown that invisibility is not the same as non-existence. The world contains structures whether or not unaided senses can reach them, and scientific instruments extend the reach of perception into those hidden layers. Another extraordinary use of light is spectroscopy. Spectroscopy works by studying how matter emits, absorbs, and interacts with different wavelengths of light. NASA's spectroscopy explainers describe it as a method that allows scientists to determine what objects are made of, how hot they are, how dense they may be, and how fast they are moving. This is one of the most powerful ideas in all of science. An object does not need to be touched directly in order to be analyzed. Light coming from it, or light that has passed through it, can carry a signature. Every atom and molecule interacts with light in specific ways, leaving patterns that can be read. In astronomy, this means starlight can reveal chemical composition. In laboratories, it means unknown substances can be identified. In planetary science, it means atmospheres can be studied across vast distances. Spectroscopy turns light into evidence. There is something almost miraculous in this, though it is entirely physical. A distant star cannot be sampled by hand, yet its light can disclose what elements are present in its outer layers. A glowing nebula can reveal its gases. A planet's atmosphere can leave faint spectral clues about its chemistry. Light becomes a messenger carrying structured information across emptiness. It does not merely tell us that something is there. Under careful interpretation, it tells us what kind of thing it is. This is one of the reasons astronomy is so deeply dependent on light. Much of what is known about the universe comes not from travel, but from reading radiation with enough precision and patience. Light also became a tool of communication. In fiber optics, signals are carried through thin strands of glass or plastic by the guidance of light itself. Britannica explains that optical fibers work through total internal reflection, which allows light to propagate through the fiber core over long distances with comparatively low attenuation. This turns light into a carrier of information in a very direct sense. Voices, images, messages, and streams of data can be encoded into optical signals and sent across cities, countries, and oceans. In earlier centuries, light revealed distant objects. In the modern age, it also became the means by which information itself is rapidly transported. The same basic physical phenomenon that produces reflection at boundaries can be engineered into a communication system of extraordinary reliability and scale. Medical science also makes extensive use of light as a revealing tool. Endoscopes rely on optical fibers to transmit images from within the body, allowing physicians to inspect regions that would otherwise require far more invasive access. Britannica specifically notes that medical instruments such as endoscopes depend on total internal reflection through optical fiber bundles to image internal organs. More broadly, many diagnostic and imaging techniques use controlled light to examine tissues, detect abnormalities, or guide procedures. In these contexts, light becomes a bridge between external observation and internal hidden structure. It makes the body readable without always needing to open it fully. This is another recurring pattern in the history of science. Once light can be directed and interpreted carefully, it becomes a gentle method of inquiry into places that were once closed. Lasers represent another major transformation. Ordinary light sources emit in broad spreads of direction and wavelength, but lasers can produce highly controlled beams with remarkable coherence and precision. That precision makes them useful in measurement, communication, surgery, manufacturing, and experimental physics. A laser is not valuable merely because it is bright. Its value lies in order. It provides light shaped for accuracy. That allows scientists and engineers to use it for alignment, ranging, data transmission, spectroscopy, delicate material processing, and countless other tasks. In this way, light becomes not just a passive signal to be received, but an actively designed probe that can interact with matter in tightly controlled ways. What ties all these uses together is a change in attitude. Human beings stopped treating light only as a natural backdrop and began treating it as something that could be disciplined into a method. A telescope gathers it, a microscope focuses it, a spectroscope separates it, a fiber guides it, a detector counts it, a laser shapes it. In every case, the aim is similar: to extract information that unaided perception could not reach. That is why light is such a central scientific tool. It can travel, carry patterns, interact selectively with matter, and be manipulated with great precision. Very few phenomena offer all of those advantages at once. Light does, and science has built entire ways of knowing around that fact. This chapter also stands apart from the earlier ones in an important way. Before this point, the story of light focused on what light is, its wave behavior, its quantum character, its role in color perception, and the way motion and gravity shape what arrives. Here, the emphasis changes from nature to use. The question is no longer only what light does by itself, but what human beings learn to do with it. That shift matters because science advances not only through theory, but through technique. Knowing that light behaves lawfully is one thing. Turning that lawful behavior into a microscope, a telescope, a spectrograph, or a fiber optic link is another. Much of modern knowledge exists because that second step was taken. Perhaps that is one of the deepest reflections this chapter invites. The invisible world was not empty before we found ways to see it. It was always there, waiting in cells, in spectra, in distant galaxies, in hidden organs, in dust-shrouded nurseries of stars, and in signals traveling silently through glass. Light gave us a way to meet those realities without dissolving the distance between us and them. It carried the evidence across, and maybe that says something quiet about human life as well. We are limited creatures, but not locked entirely inside those limits. With patience, tools, and careful interpretation, we have learned to take something as gentle as light and turn it into knowledge of things far too small, far too distant, or far too hidden for ordinary sight. For a brief time in a very large universe, matter has arranged itself into beings who can teach light to reveal what darkness once concealed. Chapter 10. Light in the Cosmos, the ancient messenger that connects you to the universe. When human beings first looked into the night sky, They did not know that almost everything they were seeing was already old. The stars seemed immediate, as if their light belonged to the present moment in the same way firelight belongs to a nearby room. But cosmic light is never that simple. It travels. It leaves stars, galaxies, nebulae, and the early universe itself, then crosses immense reaches of space before finally arriving at an eye, a detector, or a telescope. By the time it reaches us, it has already lived a history. That is why light in the cosmos is not only illumination, it is evidence, memory, and message. Astronomy, at its deepest level, is the reading of ancient light. This makes light the central link between human beings and the wider universe. We cannot travel to most of the places we study. We cannot touch stars, collect matter from distant galaxies by hand, or stand beside the first generations of cosmic structure. Yet light allows contact without physical arrival. It carries information from far beyond the reach of ordinary motion. Its color, intensity, spectrum, polarization, and direction preserve clues about where it came from and what happened to it on the way. A beam of starlight is not just brightness crossing darkness. It is a structured physical record. Through it, astronomy becomes possible. One of the first great realizations of modern astronomy was that to look farther into space is also to look farther into time. Because light has a finite speed, cosmic distance is inseparable from delay. The moon is seen not as it is in some absolute universal present, but as it was when the light now reaching us left its surface. The sun is seen in the past by a small but real interval. Distant stars are seen years after the light began traveling. Remote galaxies are seen as they were when the universe itself was younger. NASA's astronomy materials emphasize exactly this point. Deep observation is a form of time travel in the scientific sense. The farther out our telescopes reach, the earlier a chapter of cosmic history they begin to reveal. That idea becomes especially powerful when studying the earliest galaxies. NASA explains that telescopes such as the James Webb Space Telescope are designed to observe light that left the first stars and galaxies nearly the full age of cosmic history ago. Much of the ancient light has been stretched by the expansion of the universe into longer wavelengths, especially the infrared, by the time it reaches us. So when astronomers search for the young universe, they are often not looking for bright, familiar, visible light. They are looking for light that has aged in transit, altered by the history of space-time itself. The universe does not merely show us its past. It delivers that past transformed, and we learn to read the transformation. This is one reason spectra matter so much in cosmic astronomy. A spectrum is what emerges when light is spread out by wavelength, revealing structure hidden inside what otherwise looks like a simple glow. From spectra, astronomers can infer temperature, chemical composition, density, and motion. The light from a star can reveal the presence of hydrogen, helium, calcium, sodium, and many other elements because atoms interact with light in precise ways. The light from a galaxy can show whether stars are actively forming, whether hot gas is present, and whether the whole system is moving away from us. Spectroscopy turns cosmic light into language. Instead of merely seeing that something shines, astronomers learn what kind of thing is shining, what it is made of, and how it is changing. In this way, light becomes the main historical archive of the cosmos. The heavy elements now present in planets and living bodies were forged in stars and stellar explosions, and their signatures appear in light. Nebulae reveal their gases through emission. Galaxies reveal their stellar populations through broad spectral patterns. Even dust, which can hide visible light, becomes informative when observed at other wavelengths, especially in the infrared. So cosmic light is not a single channel of information. It is a layered record in which different wavelengths reveal different structures and processes. Some show hot, energetic regions. Others show cool dust, molecular clouds, or ancient red-shifted emission. The universe has many faces, and each face appears through a different conversation with light. There is also a deeper sense in which light does not merely reveal objects, but reveals cosmic evolution. The large-scale expansion of the universe leaves a measurable imprint on light through redshift. The more distant a galaxy is, in general, the more its light has been stretched by the expansion of space during its long journey. This allows astronomers to arrange observations into a kind of historical ladder, seeing galaxies not all at one age, but across different eras of development. By combining redshift measurements with imaging and spectroscopy, astronomers reconstruct how galaxies formed, merged, changed, and built up structure over cosmic time. Light is therefore not only a messenger from places, it is a messenger from epochs. Perhaps the most extraordinary example of all is the cosmic microwave background. ESA describes it as the cooled remnant of the first light that could travel freely through the universe. In the early universe, matter and radiation were coupled so tightly that photons could not move long distances without being scattered. The universe was effectively opaque. Only after the cosmos cooled enough for electrons and nuclei to combine into neutral atoms could light begin to stream freely across space. The radiation released from that transition still fills the universe today, though stretched into the microwave part of the spectrum by cosmic expansion. It is, in a literal scientific sense, fossil light. What makes the cosmic microwave background so valuable is not only its age, but its structure. ESA explains that its tiny temperature fluctuations correspond to regions of slightly different density in the early universe, and those small irregularities became the seeds of later cosmic structure. In other words, this ancient light preserves a map of the conditions from which galaxies, clusters, and the large-scale web of matter eventually emerged. To study it is to look at the universe before stars had fully taken over the sky, before galaxies matured, when the cosmos was still carrying the first readable imprint of future structure. Very few sources of light are more ancient, and none are more cosmologically revealing. Cosmic light also tells us about things that do not shine on their own in any simple way. Through gravitational lensing, the light of distant galaxies is bent by intervening mass, allowing astronomers to map the distribution of matter, including dark matter, from the distortions imposed on background sources. NORLAB and NASA both emphasize that by measuring how light has been warped, scientists can trace structure that is otherwise invisible to direct observation. This is one of the most beautiful themes in astronomy. Even when something cannot be seen by its own emitted light, it may still reveal itself through the way it changes the path of other light. The cosmos leaves signatures even where it withholds direct visibility. By this point, the broader pattern becomes clear. Light in the cosmos is not just a stream of brightness pouring from luminous objects. It is the main medium through which the universe becomes knowable across distance. It tells us what stars are made of, how galaxies move, how matter is distributed, what the early universe was like, and how cosmic history unfolded. It reveals objects, but also relationships among objects. It reveals not only sources, but journeys. A photon arriving at a detector may have carried information about nuclear reactions in a star, the chemistry of a gas cloud, the expansion of the universe, or the geometry of space-time along its path. Astronomy is so rich because light is so rich. This final chapter also completes the arc of the whole video. Earlier chapters asked what light is, how it behaves as a wave and as a quantum, how it becomes color in the brain, how it reflects, refracts, and bends under gravity, and how humans use it as a tool. Here the perspective widens. Light becomes the thread that ties all those meanings together on the largest possible scale. It is physical phenomenon, measurement standard, biological trigger, optical instrument, and cosmic archive all at once. That is why light belongs so naturally at the center of both physics and astronomy. It does not merely help us look at the universe. In a deep sense, it is how the universe reaches us. There is something quietly moving in that idea. The night sky is not a decoration hung above human life. It is a field of arrivals. Ancient photons released in stars, galaxies, and the early universe continue crossing the dark until some of them end their journeys in telescopes, instruments, and living eyes. We do not stand apart from that exchange. We are one of the places where the universe's light comes to rest long enough to be understood. And maybe that is the gentlest reflection of all. Across distances so great they resist ordinary feeling, light still finds a way to connect things. It links the early universe to the present, distant stars to the human mind, and silent space to meaning. For a brief time, you are part of that chain. The cosmos sends its ancient messages outward, and somehow, here on a small world, there are beings quiet enough to receive them. And now, my friend, as this journey through light comes to an end, I hope your mind feels a little calmer and the day feels a little farther away. If you're still awake, you can stay with me and watch another video. And if sleep is already close, then let go. Drift softly and sweet dreams among the stars.